Introduction to Regression Analysis. In the business world, the desired effect is typically driven by the impact of multiple independent variables working together, rather than by a single variable. Regression is a widely used technique and links to Pearson's R, sharing many of its assumptions, including linearity and the use of scale data.
It allows the researcher to make predictions of the likely values of the dependent variable y, from known values of independent variable x, in a simple linear regression, or from known values of a combination of independent variables, d, e, and f, in multiple linear regression.
The accuracy of the prediction depends on the strength of the correlation between the variables. Prediction is increasingly less accurate as there declines in value, but by using regression, it is possible to obtain the best possible estimate of the value of the second. Simple linear regression. Simple regression is a technique for estimating a score or observation in one variable, based on a score or observation in another variable. For example, it enables estimates to be made of y values from known values of x. Simple linear regression is based on finding the straight line on a scatter graph that fits the scatter points best. It is impossible to draw this line by hand, or estimate it by eye. This is where regression comes in. Mathematical regression procedures permit the precise line of best fit to be calculated. The equation describing this line is the regression equation, and is used to predict likely values of the dependent variable y, for particular values of the independent variable x. The line of best fit line minimizes the sum of the squared deviations from the line to the dots on the scatter graph, thus errors of prediction will be at a minimum. A predictor variable is a variable, the IV, from which a value is to be used to estimate a value on another variable, the DV. The criterion variable is a variable, the DV, the value of which is to be estimated from the value of the predictor variable, the IV. The least square solution. The mathematically calculated regression line by SPSS gives the closest fit to the points on the scatter graph, so that the sum of the deviations, d's, or differences of the actual y values denoted by scatter graph points, from the estimated y values given by the regression line, should be the minimum possible. The residual. It is the difference between what y actually is, and what we predict it to be, using our regression equation. The precise criterion. It is the sum of the squared deviations from each of the points, which is known as the least square solution. The least square solution minimizes the sum of the squared deviations from each point of the regression line. In order to specify the regression line for any scatter graph, you need to quantify two things. 1. The point at which the regression line cuts the vertical or y-axis. This is the number of units of measurement from the 0 point of the vertical axis. And 2. The slope of the regression line, or, in other words, the gradient of the best fitting line through the points on the scatter graph. Assumptions of regression. A minimum requirement is to have at least 15 times more cases than IVs. For example, with 3 IVs, you should have a minimum of 45 cases. Outliers can have considerable influence on the regression solution, and should be identified and removed as they affect the accuracy of prediction. Differences between obtained and predicted DV values should normally be distributed, and variance of residuals the same for all predicted scores, homoscedasticity. These assumptions can be tested by inspecting residual scatter graphs and histograms. Regression procedures assume that the dispersion of points is linear, where the floor amount of scatter around the line varies markedly at different points, and forms a pattern. Then the use of regression is questionable. Other issues with regression. To make predictions, it is assumed that the new individual, or the new group and the old group are both samples from the same population, since we are predicting the y-score for the new individual or group, based on the data gathered from the original group. Regression is less accurate where one variable has a small range, and the other a large range. There are always two regression lines between two variables. That from which variable y is predicted from variable x, and that from which variable x is predicted from variable y. They almost invariably have different slopes. However, life is made simpler if we always have the predictor on the horizontal axis, and the criterion to be predicted on the vertical axis. You need to be careful what you are trying to predict, and from what. there is no implication that an increase in X causes an increase in Y. Although it may appear, for example, that additional advertising caused more people to purchase their holidays from Holidays R Us, we can only conclude that X and Y move together. The simultaneous increase in X and Y may have been caused by an unknown third variable excluded from the study. Multiple regression. With more than one predictor variable, we use multiple regression. Multiple regression is a technique for estimating the value of the criterion variable from values on two or more other variables. Multiple correlation, designated R, is a measure of the correlation of one dependent variable with a combination of two or more predictor variables. In multiple regression, researchers can determine the statistical significance of both the overall multiple correlation coefficient, R, as well as for each B, or beta, individually. If the overall R is not significant, the individual B's and betas will not be tested for significance. Yet it is possible for overall R to be significant, but for some of the individual B's or betas not to be significant. For example, the overall significant correlation might be due to the strong influence of only one predictor variable, while the others have minimal contributions. The coefficient of multiple determination measures the strength of the relationship between Y and the independent variables. In multiple regression, very high correlations between IVs should be avoided. This is multicollinearity. Hierarchical and stepwise multiple regression. Sometimes researchers are interested in looking at the influence of several predictor variables in a sequential way. They want to know what the prediction will be for the first predictor variable, and then how much is added to the overall prediction by including a second predictor variable, and then perhaps how much more is added by including a third predictor variable, and so on. This is known as hierarchical multiple regression, where the researcher determines the order of entry of the IVs into the equation, based on theoretical knowledge. In the stepwise multiple correlation, the number of IVs entered, and their order of entry, is determined by statistical criteria, to produce the smallest set of predictors, that will explain the largest proportion of variance in the DV. The computer, SPSS program, goes through a step-by-step procedure, with a number of predictors, to discover the best combination of predictors. This procedure is useful to identify important variables, that can be used later in a more rigorous study. The entry method can be forward or backward. In this presentation you have learned about regression analysis. It is an essential statistical method in business, because it allows decision makers or researchers to predict certain events and values. That is, if two variables are correlated, knowledge of a value in one can be used to predict a value in the other. The more scatter there is in a scatter diagram, the less accurate the prediction will be, with prediction improving as the correlation coefficient approaches +1 and -1. In multiple regressions, two or more predictor variables are involved in predicting the score of a dependent variable. Refer back to this video throughout your course, if you are having any trouble with regression analysis.